Okay. Yeah. Hello, everybody. Good afternoon to you. It's my honor to be here. First of all, I would like to express my best gratitude to Professor Ulyanov for nice recommendation. Now, I'm going to give a talk on our recent work for sums of locally dependent random variables. That is a 3-parameter distributional approximation. Here is the outline of my talk. First of all, I briefly introduce some notions, backgrounds, and about the object of our study. After that, I'm going to state our main results in general setting. To illustrate our findings, I want to give some applications. It includes some problems in combinatorial setting and random graphs. Finally, I'm going to outline the proof our main result. Actually, a basic tool is the STEM method. This talk is based on a recent joint work with my PhD student, Xiaoling Wan. Okay, now let's begin with a basic notion, that is local dependent structure. Let G be a finite index set. Xi is a family of random integer value variables. The Xi I belongs to G is said to satisfy a classical locally dependent structure if the following three statements are satisfied. For each I, there is a subset AI such that Xi is independent of random variables outside AI. And for each I and G in AI, there is a bigger subset AIG such that Xi and Xg are independent of Xk. K is outside AIG. And still, for each I, G, and K, there is a bigger subset AIJK such that Xi, Xg, Xk are independent of random variables outside the AIJK. It is shown in this figure. There have been a lot of research work on such locally dependent structures in literature in the past years. For instance, we can find more materials in the following two papers. Now, let's define the object of our study. Denoted by W, the sum of Xi over G. Our purpose is to find a good distributional approximation for W. That is to say, find easily computed random variables Cm such that the probability of W equals to K can be approximated estimated by the probability of M equals K plus some error. Throughout my talk, we're using the total variation distance. So our goal is to control the total variation distance between W and M. So it is natural to ask, well, what is M? How small is the error? Based on the earlier works, we will use a 3-parameter random variable M to approximate W. More specifically, M will be either M1, M2, or M3. Here, M1 is the mixture of Bernoulli and Poisson random variable. M2 is the mixture of negative binomial random variable and Poisson random variable. M3 is the mixture of 3 independent Poisson distributions. So it is enough to study the total variation distance between W and MI. But now we have
a mixture or sum. What is mixture or sum? What is it?
Well, yeah. Excuse me. I'm sorry. What's your question? You mix mixture.
It is mixture of different distributions or the sum of random variables, different things.
Yeah. Here mixture. I mean the sum of independent two independent random variables. For example, M1 actually is the sum of independent Bernoulli random variable and Poisson random variable. Okay. Okay.
Thank you.
Yeah. Now we have
and pi is Poissonian. Pi is Poissonian. Yes, pi over lambda is Poissonian.
Yes, Sergey, yes.
Oh, thank you.
Yes. Okay. Now we have 2 further issues. First one is how to determine these parameters in M1, M2, or M3. A basic principle, we decide these 3 parameters in each random variable by matching their first 3 moments. That is to say, the first moment of MI is equal to the first moment of W. The second moment of MI is equal to the second moment of W. And the third moment of MI is equal to and the third moment of W. It is equivalent to net their first 3 factorial culminants match each other because it is easier to consider the factorial culminants. Recall here, the G's factorial culminant of W is defined by the following equations. In particularly, if netting MI is the ith moment of W, then it is easy to see the following identity between moments and factorial culminants. Okay. And on the other hand, by some simple calculation, we have the following factorial culminants for MI. because MI has a specific distribution, it is easy to get these formulas. Hence, the parameters in MI will be determined uniquely in an explicit way as follows. Okay? Yeah, we will decide 3 parameters for each MI by these equations. And turn to the second question. Which MI is a better candidate variable for approximating W? Recall, mu is equal, and mu stands for the first moment of W. Sigma square is the variance of W. We just compare mu and sigma square. We consider the following 3 cases separately. If the first moment of W is bigger than sigma square, we would rather use M1 to approximate the W. Okay? If mu is smaller than sigma square, we would rather use M2 to approximate the W. If mu is roughly equal to sigma square, we would rather use M3. Okay? So we will state our main result separately. We will consider these 3 different cases below. Now, I'm ready to state our main result in quite a general setting. But before that, we need some additional notations and technical terminology. First, we denote theta 1, theta 2, theta 3 by this equation. And we define S2 of W. For this, we need to introduce the second order difference, sigma delta 2, which is defined as follows. For example, delta 2H of W is equal to H of W plus 2 minus 2 H of W plus 1 minus H of W. W is a integer valued random variable, and takes the expectation with respect to W, and take the supremum over all Lipschitz function with the Lipschitz constant 1. In other words, S2 of W can be written in infinity series. And I also need some analogs of S2 of W conditioning on XAIJK. That is the definition of S2W conditioning on XAIJK, and then define SW, which is used in the upper bound of our theorem. Finally, we need another notation, gamma. Gamma is small gamma. Small gamma is actually the sum of the first 4 moments of xi. Okay. Here is an example of notation. Okay. Now we give the following theorem. We consider 3 different cases according to the size of mu and sigma. Okay. If mu is bigger than sigma square, we use M1 to approximate W. And under this case, we have the total variation distance is controlled by upper bound, which depends on some parameters and gamma SW introduced above. And similarly, we have a result in the case mu less than sigma square, and the mu approximately equal to sigma square. Okay, this is quite abstract. Yeah, sometimes we would like to use the normal random variable to approximate W. To this end, we give the following normal approximation result. Because W is an integer valued random variable, so it is better to use a discretized normal random variable YD. Yeah, YD is defined as this. Is actually YD is also integer valued random variable. The probability or probability that YD equals K is equal to the probability of a normal random variable in the interval. Okay, so as a direct consistent sequence, we have the following corollary about the approximation between W and YD. Yeah, here MI is used as an intermediate random variable, and we have the triangle inequality. So it is enough to give the second order. Here we use a result from Chen and Shaw in 2011. We have a good result. Now our paper it has been accepted for Science China Mathematics. Yeah. Now let's turn to applications. At this point, our theory might seem abstract, but in fact, it has a wide applicability. Actually, there have a few of applications in different settings. But in the following talk, I only focus on the following 4 examples. Let's start with the first one, that is counting vertices of all edges point in world. Let's consider a d-dimensional cube with the vertex set G and the edges set capital E. Assume each edge in E is assigned a random direction by tossing a fair coin. It means each edge is assigned a random direction. There are two directions. Each direction has a probability 1/2. Now define xi to be 1 if vertex I has all of its edges directed inward. Otherwise, xi is 0. For example, look at this configuration. Only one point. The has 3 edges directed inward. Now we claim xi satisfies the local dependence structure, where ai, aij, aijk are defined as follows easily. For this specific example. And then we are concerned with the number of vertices at which all the edges point inward. That is the W. So W is the sum of xi. I belongs in text set G. By some computation, we have the first 3 factorial combinations for W. As you noticed, here mu and sigma square minus mu goes to 0 as d goes to infinity. So we use M3 to approximate W. So we have the following result. The total variation distance between W and M3 is bounded by this, as in formula 2. To understand our result, we want to compare with the literature, with a paper by Artia as early as 1990. They used 1 parameter Poisson distribution to approximate W. The formula 3 is their result. So our result in this case is much better than their result. But we have to compute a 3 parameter distribution. Okay. Next is a burst problem. That is a classic problem. That is to say, put in balls into D boxes randomly with the equal probability. Fix K equal bigger than or equal to 2. Now we want to estimate the probability that at least one box receive at least the K balls. So we define the following xi. Xi equals to 1 if the balls indexed by I all go into the same box. Okay. Here I is the index, which is a subset of 1, 2, 3, n with the size K. Again, we claim xi satisfies the local dependence structure with the ai, aij, aijk defined as follows. And then we consider the sum of xi. It is easy to get the probability of xi equals K is just d power 1 minus K. And the expectation of W is this. is this. Yeah, okay. Now, we have the first factorial culminance for this W. And again, gamma 2 of W goes to 0 as D n goes to infinity. Under this assumption, under additional assumption, n power k is approximately the same as D power k minus 1. So we use M3 as before. And here is our main result. As n and d goes to infinity in such a way that we have the total variation between W and M3 is less than C times 1 over n. Yeah, our result is a significant improvement compared to the paper by Arete. Yeah, they obtained this upper bound just using 1 per meter Poisson distribution. So our result is a significant improvement of their result. And next application is counting monochromatic edges in uniformly colored graphs. Fix a graph G, yeah, with n vertices and mn edges. Di actually is the degree of vertex I, and small d is the maximum degree of this graph. Mn is the total of edges. Now each vertex is colored independently and uniformly with the Cn colors. So look at this in this configuration. In this configuration, we have 7 vertices and 11 edges, and then we colored this graph, these vertices, independently and uniformly with the 3 colors: blue, green, red, and blue. Yeah, and we define xi. I stands for 1 edge. So for hi, there are 2 vertices. Ei, for example, ei, there are 2 vertices. ei1, ei2. If ei1 and ei2 are colored the same, we define xi to be 1. Otherwise, it's 0. So in this figure, we have two edges with the same vertices, colors same. So again, we claim here xi satisfies the local dependence structure. It is easy to verify by defining ai, aij, aijk. And then we consider the sum of xi, okay? And doing some simple computation, we have the first factorial culminance for this W. But at this point, the sigma square minus mu is negative. So we would use M1 to approximate W. Yeah, the total variation distance between W and M1 is controlled by this quantity. Compared to the literature, for example, Fan and Shaw, respectively. They also consider the approximation problem between W and normal random variable. They got these two results. Compared to their results, we find our upper bound in formula 4 is reasonable and correct. And more importantly, our result is indeed better when just recall, D is the largest degree of this graph. When D is relatively small, our result looks better than their results. Finally, I want to consider the triangles in the addition random graph. This is a classical problem in random graphs. So capital G stands for a classical addition random graph with n vertices, and each edge appears with the probability 1 independently of each other edge. So xi, what is xi? Xi is equal to 1 if Ti is a triangle. Ti forms a triangle. Here Ti, just 3 vertices, is the potential triangles of this graph. So if Ti indeed exists as a triangle in random graph G, capital G and P, so it is easy to check xi satisfy the local dependence structure. Okay, and we consider the sum of triangles. Look at this example. Here n equals 2, is equal 10, p is 0.2. There are only 2 triangles in this random graph. One is 1, 4, 5. The other is 2, 5, 7. And for our W, it is easy to obtain the first factorial combinations. Now, gamma 2, as you see, gamma 2 is equal to sigma square minus mu is greater than 0 in this example. So we use M2, which is negative binomial distribution plus Poisson distribution. So we use M2 to approximate W. Assume n alpha times P goes to a positive constant. Alpha is bigger than 1/2, less than 1. Then we have the total variation distance between W and M2 is less than n power 1 minus 1 minus alpha. Is much better than the result in literature. For example, paper by Rowling and Ruth in 2015. They studied the total variation distance between W and a translated person, capital Z. But their results looks like this: a -1 plus alpha. But our result is m power of -1 minus alpha. So it's better. It's better. Okay. Finally, I would like to give a brief idea of the proof of our main result. Actually, a basic tool is the Stein method. As you know, Stein method is one of most powerful tools in estimating distance, probability in the past 50 years. Actually, Stein method first introduced by Stein, 50 years or more than 50 years ago. In order to estimate the error in the normal approximation to the distribution of a sum of dependent random variables. And shortly after, his PhD student Louis Chen in 1975 extended Stein method to get Poisson approximation for dependent trials for non-negative integer valued random graphs. Nowadays, there has been a lot of research works based on Stein method. Below is the basic frameworks. Consider two random variables, x and y, and define a distance in the sense of a function class as follows. Capital H is a function class. So the distance between x and y is the supremum of the expectation of fx minus the expectation of fy. And here, f is over the classical the function class at capital H. If h is indicate function of a, then we get the total variation distance defined above. And Stein method usually consists of the following 3 steps. Step 1 is to find a good Stein operator, such as this equation holds true. Okay. Second step is to find a solution for HF to the following so-called Stein equation. And the last step is to rewrite the distance d capital H between x and y as follows. So it's enough to consider the last inequality. In our setting, we want to consider the total variation distance between W and M. So it is enough to study the last one the last one in this slide. In this slide. Okay. Okay, that is the starting point of our study. Now, let's give the sign operator for our target variable mi. As you know, mi is specifically defined as above. So it is possible to write explicitly sign operator for each mi. Yeah, this is known in literature. As you see, there are two parts. There are two parts for each sign operator. Okay. Now, as you see, the blue part is the perturbation error part. We can use the following lemma to control the perturbation error term. As you see, for example, for M1, so so the norm delta means the difference operator. So the delta G is bounded by this quantity, which involves 3 parameters in M1. Okay. Now, I just want to give the proof of case 3. Other two cases are similar. Yeah. For the proof, we dilute by Wi. Wi is the sum of xi outside. Wi is the sum of random variables outside AI. Similarly, we can define Wijk. Yeah, let me recall. Xi is independent of Wi. Xg is independent of Wijk. Xijk is independent of Wijk. This is the required by the local dependence structure. It plays an important role in the following argument. So for M3, we have a sign method, sign operator, capital A, M3. So the expectation of this quantity can be written explicitly using the above formula. Okay. Now we want to use the Newton's expansion as follows. This formula is well known in calculus. So we use this Newton expansion for integer valued function. Okay. So the next is that we have to calculate the expectation G of W plus 1 minus G of Wi plus 1. Yeah, we just calculated the difference between these two terms. And yeah, we use the above Newton expansion to get this formula. The blue E1 is the error term. This error term is bounded by S of W, the norm of delta of G, times this expectation of Xi and plus blah, blah, blah. Yeah, this is one term. There are many other similar terms, and then combine them together. Okay. In this argument, we need a crucial observation below. This is stated as lemma 9. Yeah, in the calculation, we find this nice equality. So using this equality, we finally get our result, the final formula in this slide. Okay, but I'm sorry, I don't trouble you with many formulas, many terms. I just omit the remaining part. In summary, we have proved our main result. Okay. Yeah. Now let me stop here. Thank you very much for attention. I wish you have a new year, dragon year. Yeah. Thank you very much. I stop here.
Thank you, Professor Su, for your interesting talk. Dear colleagues, maybe you have some comments or questions. Maybe you, Professor Vladimir Ulyanov, maybe you?
Yes, yes. I have a comment, yes. First of all,
Yeah, okay.
thank you very much. Thank you very much, Professor Su, for your clear and at the same deep talk and very interesting applications. Well, and my
Yeah,
comment
thank you.
is the following. Can you open slide with theorem 4? Theorem 4.
Application 4.
Yeah, theorem 4. No,
This
theorem 4. So this is for birthday problem. Theorem 4.
I'm sorry.
Theorem
Birthday
4.
problem.
Birthday problem. Birthday problem.
Oh, birthday problem.
Stop. No. Okay, next slide. Stop. Yes.
Okay. This page.
No, before. This page. Yes, this page. Okay, so you see, the general result is quite complicated. But at the same time, when you come to applications, then the result becomes very clear. For instance, as in this theorem 4 for birthday problem. Okay? But at the same time, we can ask about maybe is it possible? No, this is my comment. This is not question.
Okay.
So one can ask, is it possible to get something similar to central limit theorem here? And the answer is yes, it's positive. It's enough to use our joint result with Babkov, which was published several years ago in Theory of Probability and its applications. And in this result, we obtained approximation for integer valued sums, on the base of normal distribution and corrections with Edger-Chebyshev terms. And this problem was solved, and it was solved jointly with Professor Su and Dr. Wang. And we put our result to archive so anybody can find it. can find it. So it's, from my point of view, it's quite interesting as well. Thank you.
Yeah, thank you. Thank you for comments.
Please, maybe another questions or comments.
Question. Such a simple question, if you don't mind. Like basically the main interesting point is that here you are dealing with basically dependent variables. Like you have a structure, dependent structure. Now,
Yes.
what would happen if we remove that property? Basically, instead of saying that those variables are dependent in some way, for example, in the way you stated, I say that they're independent. Would we get the, say, original results like related to Stein method? Or so if you look like, let's look slightly different. Like you have here W and you have X's. So basically, if you look back to Stein method, is to some extent is related to characterization problem. Now, but there in original Stein method, we are dealing with independent variables. Now I'm curious here a little bit. Indeed, it is in your work, the most important part is dealing with that dependent structure. Now,
Yes.
what kind of result we will get if we remove that dependence structure you're assuming? Thank you.
Oh. Yeah. Actually, I focused on dependent random variables. But as you know, anyway, we need some assumption about the structure, about the relations between random variables, right? Otherwise, we can get anything without any structure about the relation between random variables. Yes. So we choose to study this kind of dependence structure, that which is called nuclearly dependent structure. Yeah. So so as you see in our examples, the basic random variable are independent, and we just from HXI actually depends on underlying independent structures, but XI I mean XI itself are not independent. Yeah, so we have a nice dependent structure, right?
Yeah.
Sorry, may I make a very short comment? By the way, Tikhomirov showed that Stein method can be applied for dependent random variables in 90s. So you can find his paper, Tikhomirov, Alexander Tikhomirov.
Oh, thank you.
Thank you. 谢谢。
Yeah, 谢谢。
Professor Su, you have one question in our chat. Could you read it?
Pardon? Yeah.
You have one question from our colleague in our chat. Could you read this question and answer on it? If you can't, I can read this
Елена,
question.
you can read. You can read.
Yes, I only read it. You approximate by a mixture of binomial and Poisson, but
Mhm.
binomial has been approximated by Poisson. Why not you approximate by Poisson?
Mhm. Yeah, actually, in our study, Poisson is let me see. Let me return to. Yeah, here. The major term is, for example, M1. For example, M1. M1 is the sum of two parts. The major term is Bernoulli, a random variable. Poisson just play a perturbation term. That is, we want to adjust this parameter lambda to match with W better. So Poisson term is a small term. Lambda is a tiny parameter. So we can adjust this term so that our approximation becomes better and better. So the major term is the first Bernoulli random variable.
Is it right that maybe it's connected, that you try to match three moments? And
Yes.
in order,
Yes.
And so
We
in
want
this
to
case,
adjust these three parameters
yes.
to so that the first moments of M1 to match with the first three moments of W.
Thank you. Thank you. And maybe once more comments or questions, please. So, Professor Su, thank you so much for your very informative, by my opinion, talk. Thank you. And we will wait you on our next seminars. And I
Thank you
would
very
like
much. Thank you very much for attention. Thank you.
Thank you. And I would like to announce our next seminar. Our next seminar is devoted to mathematical statistics. The title of the talk, Goodness of Fit Tests Based on the Empirical Distribution Functions for the Parametric Distribution Families. And the talk from Professor Gennady Martynov, and we will, and now I give this name on Russian. Значит, на следующем семинаре 6 марта у нас доклад Геннадия Мартынова. Это Институт проблем передачи информации, критерии согласия, основанные на эмпирических функциях распределения для параметрических семейств распределения. Этот доклад у нас был запланирован на декабрь, и вот перенесен на март. И мы все с вами собираемся...
На 13
Да, на 13, да, как
да,
обычно.
13 число.
Да. Информация будет либо сегодня, либо завтра. Все, спасибо большое. Thank you very much for all participations of our seminar.